on to carboxylic acids. So carboxylic acids, on the right, I just have the general structure of one. They have a carbonyl group and a hydroxyl group bonded to the same carbon. This is a terminal group and usually the most oxidized functional group on the molecule. And because of the acidic hydroxyl hydrogens attached to that oxygen, it's able to hydrogen bond with other molecules. So this is a pretty reactive molecule. On the right, you can see here, attached to the carbon is a R group, usually in like an alkyl chain. Then it's also attached to a oxygen through a carbonyl, and also attached to a hydroxyl group via a single bond. So there are a few ways to make a carboxylic acid. One of the ways is through the oxidation of aldehydes or ketones using a strong oxidizing agent, or a primary alcohol as well. So if you take a primary alcohol, an aldehyde, or an it shouldn't say aldehyde and ketones, it should say aldehydes and primary alcohols. So as you can see on the bottom, if you take a primary alcohol and react it with potassium permanganate, you get a carboxylic acid. And similarly, if you take a aldehyde and you react it with a strong oxidizing agent, you can form a carboxylic acid as well. And on the bottom is just a representation of how to react a alcohol and an aldehyde to form a carboxylic acid. And since carboxylic acids are the most oxidized functional groups, you can reduce them to primary alcohols using LiAlH4, so lithium aluminum hydride. So if you take a primary alcohol and you use LiAlH4 on it, you can reduce it to primary alcohol. So this is the reverse reaction of creating a carboxylic acid. So when you use a strong oxidizing agent, you can turn a primary alcohol into a carboxylic acid. But when you react carboxylic acid with a strong reducing group, you can reform the primary alcohol. This functions as a nucleophilic addition of hydride to the carbonyl. So you add hydrogen to the carbonyl until you form water, and then that reforms the primary alcohol group. Other reducing agents like sodium aluminum hydride, it's not strong enough to reduce carboxylic acids to primary alcohols. So if you simulate, like for oxidizing agents, if you see a lot of oxygens in that reagent, you can use it as like rule of thumb. You know, oxidizing agents have a lot of oxygens. For reducing groups, usually you can tell it's a reducing group if it has a lot of hydrogens attached to it. So you can see for this lithium aluminum hydride, you can see there's 4 hydrogen atoms attached to it. So that's the reduction of carboxylic acids. So next, I'm going to go over decarboxylation. So this is when you lose a carboxyl group as carbon dioxide from a carboxylic acid. And you can do this with 1,3-dicarboxylic acids or beta-keto acids. So if there's a carbonyl group 2 carbons away from the carboxylic acid, it can spontaneously decarboxylate when heated. So as you can see here on the bottom, this beta-keto carboxylic acid, when you heat it up, you can decarboxylate the carboxyl group as carbon dioxide from the molecule. And this works with 1,3-dicarboxylic acids as well. So if it wasn't just a carbonyl group, if this carbonyl group was a carboxylic acid, you could decarboxylate either of the carboxylic acids. So this is decarboxylation of carboxylic acids. Which of the following is not capable of oxidizing a secondary alcohol to a ketone? And everyone chose choice C, and yep, that's the correct answer. So choice C, lithium aluminum hydride, it's a reducing group, and it would have no effect on a secondary alcohol, and it definitely wouldn't convert it to a ketone. While A, B, and C, those are all oxidizing groups, and they would be able to convert a secondary alcohol into a ketone. So good job, everyone.